Let me tell you something that might sound controversial. Colonizing Mars is easy. I know. Mars is 55 million kilometers away at its closest. The journey takes 7 months. The planet has no breathable atmosphere, almost no water on the surface, and temperatures that drop to minus 140 degrees. Radiation bombardment, toxic soil, dust storms that can last for months. Easy? Really? Yes. Compared to what comes next, Mars is a walk in the park, a pleasant stroll, a day trip. Because the next destination, the nearest star system beyond our own sun, is so incomprehensibly far, so impossibly difficult to reach, that it makes the Mars challenge look like crossing the street. Proxima Centauri is only 4.24 light-years away. In cosmic terms, it's our next-door neighbour, the closest star to our solar system. And reaching it is so far beyond our current capabilities that some scientists question whether it's possible at all. Today, we're going to explore why. We're going to compare the very real challenge of Mars colonization with the almost mythical challenge of interstellar travel. We're going to crunch the numbers, face the physics, and understand exactly why that small step to Mars is nothing compared to the giant leap to the stars. By the end of this video, you'll never think about space travel the same way again. Let's start with Mars. Mars orbits the Sun at an average distance of about 228 million kilometers. But planets don't sit still, and neither does Earth. The distance between Earth and Mars constantly changes as both worlds trace their elliptical paths around the Sun. At its closest approach, called opposition, Mars can be as near as 55 million kilometers. At its farthest, when Mars is on the opposite side of the Sun from Earth, the distance stretches to over 400 million kilometers. Space agencies plan their missions for the optimal launch windows, which occur roughly every 26 months when Earth and Mars are favorably aligned. During these windows, a spacecraft can reach Mars using the least amount of fuel by following a curved trajectory called a Hohmann transfer orbit. Using this efficient path, the journey to Mars takes about 7 to 9 months. The Perseverance rover, launched in July 2020, arrived at Mars in February 2021, about 7 months of travel. 7 months is a long time. It's longer than most pregnancies. It's longer than the entire Apollo 11 mission from launch to splashdown by a factor of about 50. Astronauts would spend half a year in a cramped spacecraft, exposed to cosmic radiation, their muscles and bones weakening in microgravity. But here's the thing. We've done this. Multiple times. We've sent dozens of spacecraft to Mars. We've landed rovers that have operated for years. We've mapped the entire planet in detail. We understand the challenges. Getting humans to Mars is hard, but it's an engineering problem, not a physics problem. We have the basic technology. We understand the principles. What we need is funding, commitment, and refinement. The challenges are significant but surmountable. Life support? We know how to recycle air and water. The International Space Station has been doing it for over 2 decades. We'd need to scale up and improve reliability, but the principles are understood. Radiation? A serious concern. Astronauts would receive significant doses during the transit and on the Martian surface. But shielding options exist. Water, polyethylene, even Martian regolith can block radiation. We might not eliminate the risk, but we can reduce it to acceptable levels. Landing? This is tricky. Mars has just enough atmosphere to cause problems, but not enough to help much with braking. Landing a heavy crewed spacecraft will require new techniques, supersonic retropropulsion, perhaps inflatable heat shields. But NASA and SpaceX are actively working on these challenges. Supplies? Mars has resources. Water ice exists at the poles and beneath the surface at many locations. The atmosphere is 95% carbon dioxide, which can be converted to oxygen and methane fuel. In situ resource utilization, living off the land, is challenging but achievable. Return? This is the hardest part. Getting off Mars requires manufacturing fuel on the surface, launching a vehicle, and making the 7-month journey back. It's never been done. But again, it's engineering. We know how rockets work. We know how to make fuel. We just need to do it on another planet. Every challenge of Mars colonization has a plausible solution. Some are expensive. Some require technology we haven't quite perfected. But none violate the laws of physics. None require miracles. Let me walk you through exactly how a Mars mission would work. Not in theory, in practice. Because the details reveal just how achievable this actually is. The journey begins in low Earth orbit. A crew vehicle and a transit habitat are assembled from components launched separately. The crew launches last, docking with the assembled spacecraft that will carry them to Mars. The transit habitat is about the size of a school bus, cramped but livable. It contains sleeping quarters, a galley, exercise equipment, and workstations. The crew of 4 to 6 astronauts will spend 7 months here, following a strict routine of exercise, maintenance, and scientific work. Water is recycled continuously. The ISS already achieves over 90% water recovery from urine, sweat, and humidity. For a Mars mission, this would be pushed even higher. Every drop matters. Air is maintained through a combination of stored oxygen and carbon dioxide scrubbers. Plants might be grown to supplement the system and provide fresh food. The technology exists, it just needs to be optimized for reliability. Food is primarily pre-packaged, similar to ISS rations. A 7-month supply for 6 people is substantial but manageable, a few tons including packaging. Some fresh vegetables from onboard gardens would add variety and nutrients. The spacecraft uses solar panels for electricity during most of the transit, switching to nuclear power, a small radioisotope generator during the Mars approach when solar intensity drops. Both technologies are proven. After 7 months, Mars looms ahead. Now comes the hard part, landing. Mars's atmosphere is thick enough to require a heat shield, but too thin for parachutes alone to slow a heavy craft sufficiently. NASA's Mars rovers used a combination of heat shields, parachutes, and either airbags or sky cranes. But a crewed lander is much heavier, perhaps 20 to 40 tons. The current leading solution is supersonic retropropulsion, firing rockets while still moving faster than sound to slow the descent. SpaceX has demonstrated this technique for recovering Falcon booster stages on Earth. Scaling it up for Mars is challenging but feasible. The lander touches down on a pre-selected site, probably near the equator, where temperatures are mildest and solar power is most effective. Ideally, supplies and equipment have been pre-positioned by earlier robotic missions, waiting for the crew's arrival. The first task on Mars is establishing power. Solar panels are deployed, and possibly a small nuclear reactor for reliability. Without power, nothing else works. No life support, no communication, no experiments. Next comes habitat setup. The crew might live in the lander itself initially, then expand into inflatable modules or pressurized rovers. The habitat needs to maintain Earth normal pressure, filter the toxic Martian dust, and regulate temperature through nights that drop to -80 degrees. Water is extracted from Martian ice, which exists in abundance below the surface at many locations. Drilling equipment and processing plants have been delivered in advance. The water serves for drinking, hygiene, and agriculture, and can also be split into hydrogen and oxygen, fuel and air. The atmosphere, while unbreathable, is a resource. It's 95% carbon dioxide, which can be combined with hydrogen to produce methane fuel and water through the Sabatier reaction. This is the key to returning home, manufacturing propellant on Mars rather than hauling it from Earth. Over a stay of perhaps 18 months, waiting for the next optimal return window, the crew explores, conducts experiments, tests technologies for longer-term settlement, and prepares the return vehicle. When the alignment is right, they launch. A smaller vehicle carries them from the Martian surface to orbit, where they transfer to the Earth return vehicle that's been waiting. Another 7 months, and they're home. This entire scenario is challenging. It requires precise engineering, substantial funding, and acceptance of real risk. Astronauts could die. Equipment could fail. The isolation is extreme. But notice what it doesn't require. It doesn't require any new physics. It doesn't require technologies that violate thermodynamics or relativity. Every component has been demonstrated at some scale. The Mars mission is a matter of will and resources, not possibility. This is what I mean when I say Mars is easy. Not easy in the everyday sense, it's extraordinarily difficult. But easy in the sense that we can see the path forward. We know what needs to be done. We just need to do it. Consider how quickly space travel has progressed when humanity actually commits to it. In 1957, Sputnik orbited Earth, a metal ball that beeped. 12 years later, humans walked on the Moon. In just over a decade, we went from the first satellite to footprints on another world. In 1965, Mariner 4 flew past Mars and sent back 21 blurry images, the first close-up views of another planet. 55 years later, we have rovers driving around Mars, helicopters flying through its thin atmosphere, and plans for human missions within the next decade or two. This is the pace of progress when we're motivated. When we decide something matters, we can move fast. Mars falls within this paradigm. It's hard, but it's the kind of hard we know how to tackle. It's an engineering challenge, solvable with money, effort, and time. The gap between blurry photos of Mars and humans living on Mars is about the same as the gap between first satellite and moon landing. If we commit to Mars the way we committed to the Moon, we could be there within a generation. But the gap between Mars colony and interstellar travel is qualitatively different. It's not a matter of more money, more engineers, more time. It's a matter of fundamental physics pushing against our aspirations. To understand this, let's look at the history of speed. In 1825, the first public railway opened in England. Trains could travel at about 30 kilometers per hour, faster than any human had ever moved continuously. By 1900, trains reached speeds of over 150 kilometers per hour, a factor of 5 improvement in 75 years. By 1950, jet aircraft flew at nearly 1,000 kilometers per hour, another factor of 6 or 7. By 1969, the Apollo spacecraft traveled at about 40,000 kilometers per hour on their way to the Moon, another factor of 40. Today, the Parker Solar Probe reaches speeds of nearly 700,000 kilometers per hour. Another factor of about 17. Look at that progression. Every few decades, we increased our maximum speed by a factor of 5 to 50. Consistent, impressive progress. But now notice where we are relative to the speed of light. The speed of light is about 1 billion kilometers per hour. Our fastest spacecraft travels at roughly 0.07% of that. To reach even 10% of light speed, we need to increase our velocity by a factor of about 150. That's a bigger jump than the entire history of human transportation combined. From walking pace to Parker Solar Probe is about a factor of 20,000. From Parker Solar Probe to 10% of light speed is another factor of 150 on top of that. And 10% of light speed is the minimum useful velocity for interstellar travel. To make the journey in a human lifetime, you'd want to go even faster, perhaps 50% of light speed or more. The historical trend of exponential speed improvement would need to continue for centuries before we reach interstellar relevant velocities. And there's no guarantee the trend will continue. We might be approaching fundamental limits. This is the difference between Mars and Proxima. Mars is reachable with a continuation of current trends. Proxima requires a breakthrough beyond anything we can currently project. Now let's talk about Proxima Centauri. And I want you to brace yourself, because the numbers I'm about to share are going to sound absurd. They're going to sound like I'm making them up. I promise you, I'm not. These are the actual distances, the actual times, the actual energy requirements. Proxima Centauri is 4.24 light years from Earth. A light year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second. In a year, it covers roughly 9.5 trillion kilometers. So 4.24 light years is about 40 trillion kilometers. Let me try to put that in perspective. Mars, at its closest, is 55 million kilometers away. Proxima Centauri is 40 trillion kilometers away. The ratio between these distances is about 727,000 to 1. If the journey to Mars is like walking from your front door to your mailbox, the journey to Proxima Centauri is like walking from New York to Los Angeles. 700,000 times. If the Mars journey takes 7 months, and we scaled that up by the same factor, the Proxima Centauri journey would take, let me do the math, about 42 million years. Of course, we wouldn't use the same slow Hohmann transfer orbit for an interstellar journey. We'd want to go faster, much faster. Let's see how our fastest spacecraft would do. The Parker Solar Probe, at its closest approach to the Sun, reaches speeds of about 690,000 kilometers per hour. That's about 192 kilometers per second. It's the fastest human-made object in history. At that speed, how long would it take to reach Proxima Centauri? About 6,600 years. That's longer than recorded human history. Every civilization that has ever existed, Sumer, Egypt, Rome, China, the Maya, modern nations, all of it fits within 6,000 years. You'd need to maintain a mission for longer than humans have been writing things down. But wait, you might say, the Parker Solar Probe gets its speed from falling toward the Sun. A dedicated interstellar mission could go faster. Okay, let's be generous. Let's imagine we could travel at 1% of the speed of light, about 3,000 kilometers per second, roughly 15 times faster than the Parker Solar Probe at maximum velocity. At 1% of light speed, Proxima Centauri is 424 years away. That's still about 20 generations. A mission launched today would arrive around the year 2450. The people who arrive would be the distant descendants of the people who departed, assuming the ship could sustain a population for that long. What about 10% of light speed? Now we're talking serious science fiction technology. At 10% of light speed, the journey takes about 42 years, a human lifetime. Astronauts who left in their 20s might arrive in their 60s. Difficult, but conceivable, if we could achieve 10% of light speed. But here's the problem. We can't. We're not even close. And the reasons why reveal the true magnitude of the challenge. Let me explain the energy problem. To accelerate a spacecraft, you need energy. The faster you want to go, the more energy you need. And the relationship isn't linear, it's exponential. Doubling your speed requires roughly 4 times as much energy. At relativistic speeds, speeds approaching a significant fraction of light speed, the energy requirements become astronomical. Literally astronomical. Let's run some numbers. Consider a modest spacecraft about the mass of the Space Shuttle orbiter, roughly 100 tons. To accelerate this spacecraft to 1% of light speed would require about 4.5 times 10 to the 17th joules of energy. How much energy is that? It's approximately the total energy consumption of the entire human civilization for several months. All the electricity, all the gasoline, all the natural gas, all the nuclear power. Everything humanity uses for months, concentrated into accelerating one small spacecraft. And that's just to reach 1% of light speed. Remember, at that speed, the journey still takes over 400 years. To reach 10% of light speed, you'd need about 100 times more energy, roughly the total energy consumption of human civilization for decades. To reach 50% of light speed, the energy requirements explode further due to relativistic effects. You're now talking about energy equivalents comparable to the annual energy output of the Sun. And here's the really frustrating part. You need to carry your energy with you. Unlike a car that can stop at gas stations, a spacecraft must carry all its fuel from the start. And fuel has mass. And mass requires more fuel to accelerate. This creates a vicious cycle called the tyranny of the rocket equation. For chemical rockets, the kind we use today, the math is devastating. To reach even a tiny fraction of light speed using chemical propulsion, you'd need a fuel-to-payload ratio so extreme that the spacecraft would be almost entirely fuel. A ship the size of a small moon would be needed to send a modest payload to the stars. Chemical rockets simply cannot do interstellar travel. The physics doesn't work. It's not an engineering challenge, it's a fundamental limitation. What about nuclear propulsion? Nuclear thermal rockets, where a reactor heats propellant to create thrust, are more efficient than chemical rockets. They can achieve exhaust velocities 2 or 3 times higher. NASA developed working prototypes in the 1960s and 70s. But even nuclear thermal rockets top out at exhaust velocities of around 10 kilometers per second. That's impressive for solar system exploration. It could cut Mars transit times significantly. But for interstellar travel, it's still hopelessly inadequate. The fuel ratios remain absurd. Nuclear pulse propulsion is more promising. This concept, studied in the Project Orion program, involves detonating nuclear bombs behind the spacecraft and riding the shockwaves. It sounds insane, and it is, but the physics actually works. Orion designs could theoretically achieve exhaust velocities of tens of kilometers per second, maybe even up to 3% of light speed. At 3% of light speed, Proxima Centauri is about 140 years away. Still multiple generations, but getting closer to something imaginable. The problems with Orion are political and practical rather than physical. Launching a spacecraft by detonating thousands of nuclear weapons would create significant radioactive fallout. Treaty restrictions prohibit nuclear explosions in space. And the engineering of a ship that could survive thousands of nuclear detonations is, to put it mildly, challenging. Still, Orion represents one of the few propulsion concepts that could theoretically achieve interstellar relevant speeds with technology we more or less understand. Fusion propulsion offers another possibility. If we could achieve controlled fusion, the process that powers the sun, we could create rockets with exhaust velocities of thousands of kilometers per second. Fusion rockets might reach 5 to 10% of light speed. The catch is that we haven't achieved controlled fusion yet, despite decades of trying. And even if we do, engineering a fusion reactor small and light enough to put on a spacecraft, yet powerful enough to accelerate for years, is an enormous challenge. Antimatter propulsion is the ultimate in theoretical efficiency. When matter meets antimatter, they annihilate completely, converting their entire mass to energy according to E equals mc squared. No other reaction is so efficient. An antimatter rocket could theoretically reach significant fractions of light speed with reasonable fuel ratios. The physics is beautiful. The problem is that antimatter doesn't exist naturally in any significant quantity. We have to manufacture it, atom by atom, in particle accelerators. The total amount of antimatter ever produced by humanity is measured in nanograms, billionths of a gram. To fuel an interstellar spacecraft would require tons of antimatter, which would take trillions of years to produce at current rates and cost more than the entire global GDP. Antimatter propulsion isn't impossible in principle, but it's so far beyond our current capabilities that it might as well be magic. Let me pause here and make sure you understand what we've just covered. For Mars, we have rockets that work. Chemical propulsion can get us there in 7 months. We've done it dozens of times. The challenges are about life support, landing, and sustainability. All hard engineering problems, but solvable ones. For Proxima Centauri, we don't have propulsion that works, not even close. Every technology we've discussed either can't achieve the necessary speeds, doesn't exist yet, or would require resources beyond anything humanity has ever marshaled. The gap between Mars and Proxima isn't just quantitative, it's qualitative. It's the difference between hard and impossible. But let's keep going, because propulsion is just the beginning of the problems. Let's talk about time. Even in the most optimistic scenarios, 10% of light speed, advanced propulsion, everything working perfectly, the journey to Proxima Centauri takes over 40 years. 40 years is a human lifetime. People who leave as young adults arrive as seniors. Children born during the journey would know nothing but the inside of a spacecraft. They would arrive at an alien world, never having seen Earth, never having breathed outdoor air, never having known anything beyond metal walls and recycled water. Is this psychologically sustainable? Humans evolved for open savannas, for communities, for variety and novelty. Can we survive 4 decades in a metal tube? Let me tell you about what happens to people in isolation. because this is one of the most underappreciated challenges of interstellar travel. In 1972, a French scientist named Michel Siffre spent 6 months alone in a cave in Texas. No sunlight, no clocks, no human contact. His goal was to study how the human body keeps time without external cues. Within weeks, his sense of time broke down completely. He thought he had been underground for only 2 months when 6 had passed. His sleep cycle drifted to 50 hours, 36 hours awake, followed by 14 hours of sleep. He became deeply depressed, contemplated suicide, and emerged psychologically scarred. And that was just 6 months. Alone, yes, but with the knowledge that the outside world existed, that rescue was possible, that the isolation would end. Now imagine 40 years. Not alone, you have crewmates, but confined to a space smaller than most houses, with the same people, the same walls, the same recycled air, day after day, after year, after decade. The Mars Desert Research Station in Utah conducts simulated Mars missions lasting weeks to months. Participants report significant psychological strain even in these short periods. Interpersonal conflicts emerge, cliques form, resentments fester. And the participants know they can leave at any time if things get really bad. On an interstellar mission, there's no exit. The people you launch with are the people you're stuck with for the rest of your life. If you develop a conflict with a crewmate, too bad. If someone becomes abusive or mentally ill, the community must deal with it alone. There's no evacuation, no rotation, no relief. Studies of Antarctic research stations, which experience months of isolation in harsh conditions, show elevated rates of depression, anxiety, and interpersonal conflict. Submarine crews, confined for months underwater, develop similar issues. These are among our best analogues for long-duration spaceflight, and the results are concerning. Now scale up to decades. Some researchers believe that extremely careful crew selection can mitigate these risks. Choose people who are emotionally stable, socially skilled, highly motivated, and compatible with each other. Screen out anyone with a history of mental health issues, interpersonal problems, or low stress tolerance. Maybe this would work. Maybe a carefully selected crew could maintain psychological health for 40 years in confinement. Or maybe not. Humans are adaptable, but we're not infinitely adaptable. We have needs for privacy, for novelty, for connection with larger communities that might not be fully met in a spacecraft, no matter how well designed. And what about the children? On a generation ship, children would be born into confinement. They would never know anything but metal walls and recycled air. Would they accept this as normal? Or would they rebel against a fate they never chose? Imagine being born on a generation ship, learning that your great-grandparents chose this life for you, that you will die before reaching the destination, that your only purpose is to maintain the ship and raise children who will also die in transit. Would you accept that purpose? Or would you resent it? These questions don't have easy answers. They represent genuine unknowns about human psychology that we can't fully resolve without actually attempting such missions. For Mars, the psychological challenges are serious but bounded. The isolation lasts months, not decades. The crew knows they'll return home. The psychological stresses are acute but time-limited. For interstellar travel, the psychological challenges might be insurmountable. We genuinely don't know. And we won't know until we try, by which point it's too late to turn back. We have some data from long-duration spaceflight on the ISS. from Antarctic research stations, from submarine deployments. The results are mixed. Isolation affects people differently. Some adapt, others break down. Interpersonal conflicts intensify. Depression is common. The longer the isolation, the worse these effects tend to be. 40 years is far longer than any of these analogues. We genuinely don't know if humans can psychologically endure such a journey. And if they can't, if the crew experiences mental health crises, conflicts, even violence, there's no rescue mission coming. They're on their own, years from any help. Generation ships offer an alternative. Instead of the same people making the entire journey, you send a self-sustaining population that reproduces along the way. The people who launch the ship are not the people who arrive. This solves the psychological problem of enduring decades in isolation. Each individual only experiences a normal lifespan. But it creates new problems. How large does the population need to be? Genetic diversity requires at least several hundred people to avoid inbreeding over many generations. Social stability probably requires even more. You're essentially creating a small, self-contained civilization. How do you govern such a society? What happens when factions emerge? When people disagree about the mission's purpose? When someone decides they don't want to go to Proxima anymore? On Earth, dissenters can emigrate. On a generation ship, there's nowhere to go. How do you maintain the technical knowledge needed to operate the ship? Specialized skills must be passed down through generations. If the nuclear engineering knowledge is lost, if the life support expertise dies out, the ship dies with it. You need not just a population, but a functioning educational system that reliably transmits critical knowledge for centuries. How do you maintain the ship itself? Every component has a lifespan. Seals degrade. Electronics fail. Structural members fatigue. A ship designed for a 40-year journey might, with maintenance, last 80 or 100 years. A journey lasting centuries would require not just maintenance, but essentially rebuilding the ship in flight, using only the materials you brought with you or can manufacture from raw materials. Generation ships aren't impossible, but they're not really spacecraft. They're self-sustaining worlds. The engineering requirements are closer to building a functioning country than building a vehicle. And let's not forget, even if you succeed, even if a generation ship arrives at Proxima Centauri 400 years from now, the people who arrive have no connection to the people who launched. Different language, different culture, different values. They're essentially a new civilization, related to Earth only by ancestry. Is that colonization? Or is it something else? The creation of a new branch of humanity, forever separated from the old. Now let's discuss radiation. Space is not empty. It's filled with radiation, high-energy particles from the sun, cosmic rays from distant supernovae, and background radiation from the Big Bang itself. On Earth, we're protected by our atmosphere and magnetic field, which deflect or absorb most radiation before it reaches us. Astronauts on the ISS receive elevated doses, but the station orbits within Earth's protective magnetic bubble. Mars missions would expose astronauts to serious radiation during transit and on the surface, since Mars has no global magnetic field and a thin atmosphere. This is a recognized hazard, and various shielding approaches are being studied. The exposure would increase cancer risk, but probably not be immediately lethal. It's a problem, but a manageable one. Interstellar space is far more hostile. Outside the protective influence of the Sun, a region called the heliosphere, cosmic ray intensity increases significantly. High-energy particles from across the galaxy bombard anything in their path. Over a journey of decades, the cumulative radiation dose would be severe. Shielding helps, but there's a catch. The most energetic cosmic rays can penetrate meters of material. When they hit shielding, they can create secondary radiation, cascades of particles that can be more dangerous than the original ray. Simply piling on more shielding doesn't always help, and can sometimes make things worse. Effective protection against galactic cosmic rays might require active shielding, magnetic fields strong enough to deflect charged particles, similar to how Earth's magnetic field protects us. Creating such fields around a spacecraft is technically challenging and energy-intensive. It might be possible, but it adds yet another layer of complexity to an already impossible list. Without adequate protection, the crew of an interstellar mission would accumulate radiation damage over the decades of travel. Cancer rates would skyrocket. Cognitive function might degrade. Reproductive capacity could be compromised. A generation ship might find that later generations suffer increasing genetic damage, threatening the viability of the entire population. This is another problem that doesn't really exist for Mars missions. The exposure is limited to months, not decades. Shielding can be provided. The risk, while real, is acceptable. For interstellar travel, the risk is existential. Let's talk about communication. When Perseverance landed on Mars, the signal announcing its arrival took about 11 minutes to reach Earth. At maximum distance, Mars communications experience a delay of over 20 minutes each way. This is annoying for mission controllers, but manageable. Instructions can be planned in advance. Rovers can be given some autonomy. Proxima Centauri is 4.24 light-years away. A signal traveling at light speed takes 4.24 years to make the journey. A round-trip communication, sending a message and receiving a reply, takes 8.5 years. Think about what that means. If you send a distress call, help cannot even know about your emergency for over 4 years. Any response would arrive more than 8 years after you called. If you ask a question, you wait nearly a decade for an answer. If you report a discovery, the people who launched you might be dead by the time your message arrives. For a Mars colony, Earth can provide support, expertise, consultation. Problems can be discussed and solutions sent. Supplies can be dispatched. There's a meaningful connection between the colony and the home world. For an interstellar mission, Earth becomes irrelevant. The time lag is so extreme that no practical assistance is possible. The ship must be entirely self-sufficient, capable of handling any emergency, solving any problem, using only the resources and knowledge aboard. This isn't just a technical requirement, it's a philosophical shift. A Mars colony is an outpost of Earth, dependent and connected. An interstellar mission is a separate civilization, isolated and autonomous. Now let's consider what happens when you arrive. You've traveled for 40 years. You've survived radiation, isolation, the psychological strain of decades in a metal box. You've crossed 40 trillion kilometers of void, and finally, Proxima Centauri looms ahead. There's just one problem. You're still moving at 10% of the speed of light. At that velocity, you would cross the entire Proxima system in about a day. You'd blow past any planets without time to enter orbit, let alone land. All that effort, all that time, and you'd just miss. To actually stop at your destination, you need to decelerate. And deceleration, in space, requires exactly as much energy as acceleration. Whatever miracle propulsion system got you up to speed, you need to use it again to slow down. If you're using rockets, this means carrying enough fuel not just to accelerate, but also to decelerate. The rocket equation becomes even more punishing. Your fuel requirements roughly double, which in practical terms means they increase by far more than double due to the exponential nature of the equation. Some proposals try to avoid this problem. Breakthrough Starshot, a concept we'll discuss later, plans to send tiny probes that don't decelerate at all. They would fly through the Proxima system at 20% of light speed, taking pictures as they pass, then continue into the void forever. It's a flyby, not a visit. For human missions, flyby isn't acceptable. You need to stop. You need to enter orbit. You need to land. Each of these steps requires energy, fuel, precision, and technology we don't have. And once you've arrived, then what? Proxima b, the planet orbiting Proxima Centauri in the habitable zone, is likely nothing like Earth. It's probably tidally locked, with one face permanently toward its star and one face permanently in darkness. The star itself, a red dwarf, emits frequent powerful flares that may strip away atmosphere and bombard the surface with radiation. Let me paint you a picture of what arriving at Proxima might actually look like. You've traveled for decades. Your ship is showing its age. Systems that were state-of-the-art at launch are now ancient, maintained by hand-manufactured replacement parts and jury-rigged repairs. The original crew is dead or elderly. Their grandchildren, born in transit, have never seen a planet. As you approach, your telescopes reveal Proxima b in detail for the first time. What you see is not encouraging. The planet is larger than Earth, perhaps 1.3 times the mass. That means higher gravity. Anyone who lands will feel noticeably heavier, and the colonists born on the ship in microgravity will struggle even more. One hemisphere faces the star permanently, baked by radiation and flares. The other hemisphere faces away, locked in eternal frozen darkness. Between them lies the Terminator Zone, a ring of perpetual twilight where temperatures might, possibly, be survivable. But the atmosphere is thin, if it exists at all. Proxima Centauri's frequent flares may have stripped it away over billions of years. Without an atmosphere, there's no protection from stellar radiation, no greenhouse warming, no breathable air. The surface might be entirely frozen on the dark side, entirely molten on the light side, with only a narrow band in between where liquid water could exist. If there's any water at all. And there's another problem you didn't anticipate. The planet has no magnetic field. Without that invisible shield, even the Terminator Zone is bombarded by charged particles from the star. Cancer rates among any colonists would be catastrophic. Your ship carries supplies for perhaps 10 years of independent operation. After that, you need to be self-sufficient. But self-sufficiency requires resources: water, metals, organic compounds, energy. If Proxima b lacks these resources, if it's an airless, waterless rock bathed in radiation, your colony is doomed. All those decades of travel, all those generations of sacrifice, for nothing. This is the gamble of interstellar colonization. You're betting everything on a destination you can barely see, hoping it offers what you need to survive. There's no backup plan. There's no return ticket. At least with Mars, we know what we're getting. We've mapped it. We've analyzed its soil. We've measured its radiation. We understand its seasons, its dust storms, its ice deposits. We go in with open eyes. For Proxima, we're essentially blind. We're sending our descendants into the unknown, trusting that the universe will provide. Maybe it will. Maybe Proxima b has liquid water oceans in the Terminator zone, sheltered from radiation by thick ice caps. Maybe it has geothermal energy and mineral resources. Maybe it's survivable. Or maybe it's not. Maybe it's a death trap. And we won't know until people have already committed their lives to finding out. There might be no breathable air. There might be no liquid water on the surface. The habitable zone means only that liquid water is theoretically possible, not that conditions are actually friendly to life. Colonizing Proxima b might make Mars look like a tropical paradise. At least on Mars we know what we're dealing with. At least on Mars we've done reconnaissance. At Proxima, we'd be arriving after decades of travel to a world we've barely glimpsed through telescopes, hoping it's survivable, with no possibility of turning back. Let me now run through a direct comparison to make the contrast absolutely clear. Distance. Mars, 55 to 400 million kilometers. Proxima, 40 trillion kilometers. Ratio, roughly 100,000 to 1. Travel time with current technology. Mars, 7 to 9 months. Proxima, tens of thousands of years. Ratio, roughly 200,000 to 1. Travel time with optimistic future technology. Mars, 3 to 4 months with advanced propulsion. Proxima, 40 to 400 years. Ratio, roughly 1,000 to 1. Communication delay. Mars, 3 to 22 minutes. Proxima, 4.24 years. Ratio, roughly 100,000 to 1. Possibility of resupply. Mars, yes, every 26 months. Proxima, no. Possibility of return. Mars, difficult but feasible. Proxima, essentially impossible with any near-term technology. Possibility of rescue. Mars, possible in emergencies. Proxima, none. Prior reconnaissance. Mars, extensive. Dozens of orbiters, landers and rovers. Proxima, none. Telescopic observations only. Every single metric shows a difference of at least 3 orders of magnitude, a factor of 1,000 or more. Many show differences of 5 orders of magnitude, a factor of 100,000. This is not a difference of degree, it's a difference of kind. Mars is a destination. Proxima is a dream. But dreams matter. So let's talk about what might, someday, make interstellar travel possible. The most serious near-term proposal is Breakthrough Starshot. Funded by billionaire Yuri Milner and supported by scientists including the late Stephen Hawking, Starshot aims to send tiny spacecraft to Alpha Centauri within a generation. The concept is elegant in its simplicity. Instead of trying to accelerate a large, crude spacecraft, you accelerate something tiny, a chip weighing just a few grams, attached to a thin, reflective sail. The propulsion comes not from onboard fuel, but from a massive array of ground-based lasers. These lasers would focus on the sail, pushing it with the pressure of light. With about 100 gigawatts of laser power, roughly the output of 100 nuclear power plants, the tiny probe could be accelerated to 20% of light speed in about 10 minutes. At that velocity, Proxima Centauri is just 20 years away. The probes would carry miniaturized cameras, communication equipment, and possibly simple sensors. They would fly through the Proxima system, snap pictures, and transmit data back to Earth via tiny onboard lasers. The first images of planets around another star could arrive within 25 to 30 years of launch. This is not science fiction. The physics works. The individual technologies exist, though they've never been combined at this scale. Starshot is funded and actively in development. But notice what Starshot is not. It's not colonization. It's not even visitation. It's a flyby mission using gram-scale probes. The spacecraft are too small to carry humans, too fast to stop, too simple to do more than take pictures. Starshot is the interstellar equivalent of throwing a pebble across a canyon. It proves the distance can be crossed, but it doesn't build a bridge. For human travel, we need something else. The most commonly discussed concept is the generation ship, which we've already explored. A self-sustaining vessel carrying a population that reproduces during the journey, arriving at the destination centuries after departure. Generation ships face the challenges we've discussed: population genetics, social stability, knowledge transmission, maintenance, radiation. They also face the propulsion problem. Even a generation ship needs to achieve a reasonable fraction of light speed to arrive within 1,000 years. The most favourable designs assume nuclear pulse propulsion or fusion drives, achieving perhaps 5% of light speed. At that velocity, Proxima is about 85 years away, still requiring multiple generations, but at least limiting the voyage to a few rather than a dozen. Building a ship capable of sustaining a population for 85 years is enormously difficult, but perhaps not impossible. The scale would be unprecedented, essentially a small city in space, but the individual components are not beyond imagination. The political and economic will to build such a ship is another matter. The cost would be measured in trillions of dollars. The commitment would span generations. The benefit to those who fund it would be essentially zero. They would never see the results. Humans are not good at multi-generational projects. We struggle to address climate change on a timescale of decades. Building a generation ship would require planning on a timescale of centuries. Another approach avoids the biological challenges by sending only machines. Robotic probes don't need life support. They don't experience loneliness or interpersonal conflict. They can be put in standby mode during transit, avoiding the wear of continuous operation. They can be designed to self-repair or self-replicate at the destination. A robotic interstellar mission would still face the propulsion challenge, but without the mass penalty of human habitation. A probe massing just a few hundred kilograms might be achievable with advanced propulsion systems. Upon arrival, such a probe could explore the destination system, identify promising sites, and prepare the way for future human missions, or for robot missions that would extract resources and build infrastructure. Some visionaries imagine self-replicating probes, machines that could arrive at a star system, mine asteroids, build copies of themselves, and send those copies to further stars. Over millions of years, such probes could spread throughout the galaxy exponentially. This concept, sometimes called a von Neumann probe after mathematician John von Neumann, would allow exploration of the entire galaxy without requiring faster-than-light travel. The speed of light remains a barrier, but patience and self-replication overcome it. The timescales are vast, millions of years to fully explore the Milky Way, but cosmic time is patient. If we launched von Neumann probes and then went extinct, our robotic descendants might still spread to every star, carrying the memory of their creators. There's something both hopeful and melancholy about this vision. We might never see the stars ourselves, but something we made might carry our legacy there. Sleep ships offer another approach. If we could place humans in suspended animation, slowing their metabolism to near zero, we could eliminate the psychological challenges of long-duration travel. The passengers would experience the journey as a single extended sleep, waking at the destination as if no time had passed. We don't currently know how to do this. Cryonics, the practice of freezing bodies after death for potential future revival, exists but is unproven. We have no evidence that a frozen brain can be successfully revived. Suspended animation in living humans remains science fiction. However, biology offers hints that it might be possible. Some animals hibernate for months. Certain frogs survive freezing solid. Tardigrades can enter a cryptobiotic state, shutting down metabolism almost completely, and revive after years or even decades. If we could induce a similar state in humans, interstellar travel becomes more feasible. A sleep ship could be smaller than a generation ship, since the passengers wouldn't need living space, food, or entertainment during transit. The journey could last centuries without psychological harm. The challenges are biological and medical, rather than physical. We need to learn how to pause human metabolism and restart it safely. This might require advances in our understanding of biochemistry, neuroscience, and aging that are decades or centuries away. Digital minds represent perhaps the most radical approach. If consciousness can be uploaded to a computer, if the pattern of neural connections that defines a person can be copied into software, then interstellar travel becomes almost trivially easy. A digital mind doesn't need food, water, or air. It doesn't age. It can be copied, backed up, and transmitted. It can run at different speeds, experiencing the journey as a brief interval or as an extended lifetime. It can operate in virtual environments indistinguishable from physical reality. A digital mission could be tiny. A chip containing millions of uploaded minds could be accelerated to relativistic speeds with minimal energy. The passengers would experience the journey in virtual paradise, emerging into robot bodies at the destination. Of course, we don't know if consciousness can be uploaded. We don't understand consciousness well enough to be confident that copying neural patterns would preserve subjective experience. The uploaded entity might be a philosophical zombie, behaving like the original but lacking inner experience. And there are profound ethical questions. Is an uploaded mind really you? Or is it a copy that remembers being you? If you upload, and then the original body continues living, are there now two of you? If the upload is deleted, is that murder? These questions are fascinating, but unanswerable with current knowledge. Digital minds remain firmly in the realm of speculation. Let me step back and address a question you might be asking. Why does this matter? If interstellar travel is so hard, why bother thinking about it? Why not focus on Mars, which is achievable, and leave the stars for future generations? There are several answers, but first, let me give you some concrete numbers. Because understanding the scale of investment helps clarify what's realistic. A crewed Mars mission, according to NASA estimates, would cost somewhere between $100 billion and $500 billion over several decades of development and operation. That's a lot of money, roughly equivalent to the total cost of the International Space Station program or the Apollo program adjusted for inflation. But it's achievable. It's within the range of what major nations can fund if they choose to. The United States spends roughly $700 billion per year on defense. The entire world spends trillions annually on various priorities. A Mars program spread over 20 years would cost perhaps 20 to 25 billion per year. Significant, but not impossible. SpaceX claims it can do it for less, perhaps tens of billions rather than hundreds, by using reusable rockets and lean engineering. Whether this is realistic remains to be seen, but even the skeptics don't argue that Mars is beyond economic reach. Now consider interstellar travel. Project Daedalus, a 1970s study by the British Interplanetary Society, designed a fusion-powered probe that could reach Barnard's star in about 50 years. The estimated cost in today's dollars would be measured in trillions, comparable to the entire annual GDP of major nations. And Daedalus was just a probe. No humans, no return trip. Just a flyby to take pictures. A generation ship capable of carrying thousands of colonists. The cost estimates range from tens of trillions to hundreds of trillions of dollars. The construction would require industrial capacity beyond anything humanity has ever assembled. The timeline would span centuries. To put this in perspective, the total value of all goods and services produced by humanity in a year is roughly $100 trillion. A generation ship might cost several years' worth of the entire planet's economic output. This isn't impossible in principle. If humanity united behind a single goal, pooled resources across generations, and accepted sacrifices that dwarf anything in history, we might build such a ship. But realistically, it's not going to happen anytime soon. We can't agree on how to address climate change, which threatens us within decades. We're not going to unite behind a project whose benefits arrive in centuries. Mars is different. Mars can be funded by a single nation or a coalition of space agencies. Mars provides returns within a human lifetime, scientific discoveries, technological spin-offs, national prestige. Mars is politically achievable in a way that interstellar travel is not. This is another reason why Mars matters. It's not just technically easier, it's economically and politically easier. It can actually happen. First, thinking about interstellar travel clarifies our understanding of what's possible. It forces us to confront the true scale of the universe, the true limitations of physics, the true difficulty of cosmic expansion. This is valuable knowledge, regardless of whether we ever make the journey. Second, even if we can't reach the stars in our lifetimes, we can lay groundwork. We can develop propulsion technologies, study long-duration spaceflight, build robotic probes, and gather data about nearby star systems. Each step brings the destination a little closer. Third, humanity's survival may eventually depend on spreading beyond Earth. Our planet faces many risks: asteroid impacts, supervolcanic eruptions, climate change, nuclear war, engineered pandemics. A species confined to one world is vulnerable. A species spread across multiple worlds is more resilient. And ultimately, a species spread across multiple star systems would be nearly impossible to extinguish. This is a long-term argument. The threats are probabilistic and might not materialize for thousands or millions of years. But thinking on these timescales is precisely what interstellar planning requires. Fourth, there's the matter of meaning. Humans are explorers. We crossed oceans, climbed mountains, ventured to the poles. We went to the moon. The drive to explore is deep in our nature. The stars represent the ultimate frontier. Even if we never reach them, aspiring to reach them elevates our civilization. It gives us a goal beyond immediate concerns, a dream beyond individual lifetimes. Mars is achievable. The stars may not be. But pursuing the impossible has a way of making the merely difficult seem routine. Let me address one more comparison between Mars and interstellar travel. When we colonize Mars, we will still be one civilization. Communications are delayed but possible. Trade in physical goods is expensive but feasible. Culture can be shared. News can be exchanged. A person born on Mars might visit Earth and vice versa. Mars will be an extension of human civilization, not a separate branch. Different, certainly, adapted to new conditions, but recognizably part of the same story. Interstellar colonization is different. A colony at Proxima Centauri, even with advanced communication, would exchange messages on a timescale of nearly a decade per round trip. Meaningful conversation is impossible. Shared culture would diverge rapidly. Within a few generations, Terran humans and Proximan humans would be as alien to each other as any two civilizations in history. And if the colonists modify themselves, genetically adapting to local conditions, cybernetically enhancing their capabilities, culturally evolving in isolation, they might become genuinely different species within a few thousand years. This isn't necessarily bad, it's simply different. Interstellar colonization wouldn't spread human civilization across the galaxy. It would create new civilizations, each isolated, each evolving independently, related by ancestry, but not by continuous connection. The galaxy might eventually be filled with descendants of Earth, but they wouldn't be a unified humanity. There'd be a diaspora of separately evolved intelligences, as different from each other as we are from chimpanzees, united only by a shared genetic heritage. This is a profound transformation, and we should be clear-eyed about it. Interstellar expansion doesn't preserve humanity in any simple sense. It transforms humanity into something new. Maybe that's the point. Maybe the purpose of intelligence is to spread, diversify, and evolve, not to preserve any particular form. Maybe the galaxy should be filled with our descendants, even if those descendants would be unrecognizable to us. There's a beautiful and terrible vision here that's worth contemplating. Imagine, 1,000,000 years from now, that countless worlds across the galaxy harbor life descended from Earth. Some are recognizably human, bipedal, warm-blooded, speaking languages evolved from our own. Others have adapted to alien environments, becoming something new. Aquatic beings on ocean worlds, winged creatures on low-gravity moons, silicon-based intelligences merged with their machines. They share a common origin, but have diverged beyond recognition. They are all, in some sense, our children, but they are not us. They are something new. Some might have forgotten Earth entirely, their origin lost to time and distance. Others might remember, preserving records of the mother world as a kind of religion or mythology. Long ago, in a galaxy far away, there was a blue planet. This is what interstellar expansion might actually mean. Not a unified humanity spreading across the stars, but a diaspora of evolved intelligences, each adapted to its own world, each following its own path, united only by the distant memory of a common beginning. Is this a future worth pursuing? That depends on how you think about identity and continuity. If what matters is the survival and spread of human genes, then yes, even unrecognizable descendants still carry our DNA, still represent evolutionary success. If what matters is the survival of human culture, the answer is less clear. Culture changes, languages die, religions transform. Even without interstellar travel, the culture of the future will be vastly different from ours. interstellar distances would simply accelerate that divergence. If what matters is connection, the ability of future humans to know each other, communicate, share experiences, then interstellar expansion is a kind of tragedy. It creates new humans, but isolates them forever. There are no right answers here. These are questions of value, not fact. What do we want humanity's future to look like? What are we willing to sacrifice to achieve it? Mars offers a different kind of future. A Mars colony would remain connected to Earth, delayed by minutes, not years. Culture would diverge, but not rupture. Martians and Earthlings would be different, but still recognizable to each other, still able to exchange ideas and artifacts, still part of a single human civilization. This might be humanity's realistic future. A solar system civilization, diverse but connected, spanning multiple worlds but sharing a common identity. Not as dramatic as interstellar expansion, but perhaps more achievable and more coherent. Or maybe we'll find a way to do both. Maybe we'll spread through the solar system first, develop technologies and social structures that make interstellar travel feasible, and then reach for the stars from a position of strength rather than desperation. The first step either way is Mars. It's the proving ground, the test case, the foundation. Or maybe we should be more cautious. Maybe some caution is warranted before we irreversibly launch a process that will fragment our species forever. These are questions without easy answers. They're questions we'll need to grapple with if interstellar travel ever becomes possible. For now, let's return to Earth. Or rather, let's return to Mars. Mars is the next step. It's hard, but it's achievable. It will teach us how to live on another world, how to build self-sustaining habitats, how to survive without Earth's constant support. Let me tell you what's happening right now as you watch this video. SpaceX is building Starship, the largest rocket ever constructed. It's designed from the ground up for Mars missions. The fully reusable design promises to dramatically reduce launch costs. The heavy lift capability allows payloads of 100 tons or more to reach Mars. Elon Musk has stated his goal is to land humans on Mars by the early 2030s and to establish a self-sustaining city of 1 million people within this century. Whether you believe his timelines or not, the engineering is real. Starship has already flown to space. The pieces are coming together. NASA's Artemis program is returning humans to the Moon, in part as a stepping stone to Mars. The Gateway station, planned for lunar orbit, will test deep space habitation technologies. The technologies developed for Artemis, spacesuits, life support, power systems, will feed directly into Mars mission planning. China has announced ambitions for crewed Mars missions in the 2030s or 2040s. Their lunar program is progressing rapidly, and Mars is clearly in their sights. The United Arab Emirates, India, and other nations have sent probes to Mars. The democratization of planetary exploration is accelerating. Private companies are developing crucial technologies: in-space refueling, advanced life support, radiation shielding, nuclear propulsion. The ecosystem of Mars-related development is broader and more active than at any point in history. This is not science fiction. This is happening. The question is not whether humans will reach Mars, but when. Most experts believe it will happen within the next 20 to 30 years. Some think sooner. Contrast this with interstellar travel. There is no Starship equivalent being built for interstellar journeys. There is no government program aimed at reaching other stars. The Breakthrough Starshot project is funded and active, but it's working on gram-scale probes, not human transportation. No serious timeline exists for human interstellar travel. Not 20 years, not 50 years, not 100 years. The most optimistic projections put even robotic missions at decades away, and crewed missions at centuries or millennia. This is the concrete difference. Mars has programs, budgets, timelines, hardware under construction. Interstellar travel has concepts, studies, and dreams. Dreams matter. They motivate us and guide our long-term thinking. But they don't put humans on other worlds. Programs do. Hardware does. Funding does. Mars has all of these. The stars have none. Every lesson we learn on Mars will be relevant to interstellar travel, even if the scale is different. Life support, radiation protection, closed-loop ecosystems, psychological resilience, long-duration spaceflight. All of these must be mastered for Mars, and all of them will be needed for the stars. Mars is the training ground. It's the place where we develop the capabilities that might, someday, make interstellar travel possible. And even if we never reach the stars, Mars is valuable in itself. A second world for humanity. An insurance policy against catastrophe. A new frontier for science, exploration, and growth. We should go to Mars, not as an end in itself, but as a beginning. The first step on a journey that might, eventually, lead to the stars. Will we ever reach Proxima Centauri? I don't know. The challenges are immense. The physics is unforgiving. Every solution we've discussed has fatal problems or requires technology that doesn't exist. But I refuse to say never. History is full of impossibilities that became routine. Heavier-than-air flight was impossible. Breaking the sound barrier was impossible. Landing on the moon was impossible, until they weren't. Maybe interstellar travel is different. Maybe it's a true barrier, not just a difficult problem. Maybe the universe has set a speed limit that cannot be evaded, a distance that cannot be crossed, a frontier that cannot be reached. Or maybe we simply haven't been clever enough yet. Maybe some future breakthrough, in physics, in engineering, in biology, will open doors we can't currently see. The history of science is a history of surprises. But I won't bet on miracles. I'll bet on the achievable. And right now, the achievable is Mars. I don't know. Neither does anyone else. The future is unwritten. What I do know is this. The universe is vast beyond comprehension, and we are small. But our curiosity is enormous, and our determination is fierce. We have already crossed oceans, reached the moon, and sent robots to the edge of interstellar space. Mars is next. It's achievable. It's coming. The stars will be harder, perhaps impossibly harder, but the attempt is worth making, even if we fail. Because reaching for the stars, even if we fall short, lifts us higher than staying on the ground. Let me leave you with a final thought. Right now, as you watch this video, the light from Proxima Centauri is crossing the void toward Earth. Photons that left that star 4 years and 3 months ago are just now arriving, carrying information about a world we can never visit with current technology. But those photons are also a promise. They're a reminder that the universe extends beyond our reach, but not beyond our knowledge. We can study Proxima even if we can't visit it. We can learn about it even if we can't touch it. And maybe, someday, some future generation will watch a similar video, except they'll be watching it on a ship, halfway through a voyage to a new star, looking forward to arrival rather than dreaming of departure. I hope so. I really do. Until then, there's Mars, there's the Moon, there's the solar system with its many worlds and moons and asteroids, all within reach, all waiting to be explored. The stars are hard, but the first steps are easy. Let's take them. Thank you for watching. If this video changed how you think about space exploration, consider subscribing. We cover the hardest questions about the universe and our place in it. The cosmos is vast. Let's explore it together. And remember, the journey of 1,000 light years begins with a single step. That step is Mars. So when you look up at the night sky tonight, find Mars, that reddish point of light, our next destination. It's waiting for us. It's achievable. It's the future we can actually build. And then look a little farther, toward the constellation Centaurus if you're in the southern hemisphere. Proxima Centauri is there, invisible to the naked eye, but present nonetheless. A reminder of how much farther we have to go, a dream for future generations to pursue. The easy destination and the impossible one, both calling to us, both part of our cosmic future, one step at a time. See you there.